All right, the first question we have today is a homework question. It comes from the book problem where you've got two unequal tensions. And I don't have the number of this off the top of my head, but the picture is like this. You have ropes of unequal angles. So that's 20 degrees, and that's 30 degrees. And then the beam, some mass M. The particular one that I got was 1,100 kilograms. And so the question is, what's the tension in the string? So now this is a case where you have unequal tensions. And so the free body diagram is going to look a little bit different. What's still the same are the two components of the tensions, but are in the x directions. And they both have to add up to 1,100 in the y direction, but it's not going to be that simple. So let's draw the free body diagram. Yeah. So yeah, mg straight down. And now we have to be careful and call which one. Let's call the one left T1. Hopefully you're drawing this out as you're doing these problems. Call this one T2. Sure enough, F net still does equal 0. So that's the free body diagram. So we can sum the forces then, and then go to work on the algebra of it. So let's be completely general. We can keep the angles, but I'm just going to write them out as there are theta 1 and theta 2. So in the x direction, we have minus T1 sine of theta 1 plus T2 sine theta 2 equals 0. And then in the y direction, both the tensions are positive, so it's plus T1 cosine theta 1 plus T2 cosine theta 2 minus mg equals 0. So if you look at this equation, or so if you look at these two equations, I mean, I'm writing it in simples, and that's really, like I said, like I've been telling some people, that's a skill that we're going to have to get better at, is writing everything out in symbols. But you can technically see that since we know theta and since we know the mass and gravity, or rather the free fall constant, this is really just two equations, two unknowns. And how we get rid of them is, since we have these sines and cosines, I mean, we can still do a simple substitution method. So I'll show you what I would do in looking at these problems. If I wanted to solve for T2, if I wanted to solve for T2, I'd probably say multiply the bottom part by cosine theta 2, and the top one by sine of theta 2. That way, when I add these together, I get 1, just T2. You can just do the regular old substitution method, which, say for the x, you can solve for T1 in terms of T2, and then plug that into there to solve for T2. So it's really up to you. We could just do the basic case. Let's say that T1, if we solve for T1, T1 equals T2, and then you look at these ratios, you have sine of theta 2 divided by sine of theta 1, excuse me. Sine theta 2 divided by sine theta 1. And so I can plug that into here. And so we'll get an expression. So y becomes just an expression of T2 by itself. This will be plus T2 sine theta 2 over sine theta 1 times cosine of theta 1. That is plus T2, just get that right, that looking better, plus T2 cosine theta 2 equals mg. And so at this point, you can just factor out the T2 and divide by everything else. You get something that's not, well, it's not super simple, certainly the answer. So we've got, let's see, we've got, that turns into a cotangent actually. So that is mg pulling out the T2 and the dividing it. This is cotangent of theta 1 times sine of theta 2. So the bottom part will be sine of theta 2 cotangent theta 1 plus cosine theta 2. It's all over mg. So this is trying to keep it as general as I can. If you just stuck with the numbers, cosine of, I mean, even if you just stuck with the numbers, you'd probably still have to do something like this because, well, in order to solve for them, that's what you have to do. And so that's T2, and then T1 would be, well, it's just T2 times the ratio of the sines. And so you'll get some of these sines to cancel, or these trigonometric sines, and you'll probably get like a tangent. The tangent will probably fall out. So T1, you know, is just found by mg. It's all this times the ratio of the sines, which it looks like the sine, it should be something symmetric, but when you multiply by sine of theta 2 over, yeah, when you multiply by sine theta 2 over sine theta 1, you'll get it should become cotangent is cosine over sine. So you should get something symmetric. But I'll let you work that out. That's part of the homework problem. All right, so that is that problem. Anybody have any questions on it? All right, well, if nothing else, then let's just kind of continue with some other problems dealing with mass, weight, and gravity. I'll go ahead and save this. I meant to post this yesterday. My second class, or sorry, my evening class actually got canceled because, well, we had a big boom and we didn't have power for a couple hours. Literally 15 minutes before my class was supposed to start, we just heard this huge boom, and you know, there was no power for 2 hours. The power didn't come on until about 7:45. So let me remind you just really quickly of section 6.3 before I jump into more problems. I don't know how worth it this will be. Let's see right here. Yeah. So in the section 6.3, they distinguish between mass, weight, and gravity. And the first one that they say is that mass is an intrinsic property of an object. What does that mean? That means that it's the same value anywhere. It's the same value anywhere on Earth. It's the same value when you go up in orbit, when you go to a different planet, when you're in deep space, when you're near the sun, when you're in an elevator up or down. That's the thing that stays the same. And I would actually take it a step further and kind of zoom in like on this part right here and just do a quick little annotation to ask, yeah, probably need to make sure I got the right font on. How do you measure the mass of an object? They have a method here about a pan balance, but say you were in deep space, how would you measure the mass of an object? If there's no gravity, then you can't use, while this pan balance, or sometimes we'll use like a triple beam balance. We got the triple beam balances in the labs. Both of those use the fact that gravity is pulling it down on either side. So there's equal torques and those balances. So it still has something to do with gravity, but in deep space, this would never work. One suggestion to measure the mass of an object would be connected to a spring and see how it oscillates back and forth and measure its period. Its period, if you know the stiffness in the spring, by a spring constant, it turns out the period of oscillation is, let's see, it's 2 pi divided by root k over m. Either root m or root k. Okay, so you could solve for the mass here, and if you know that, like I said, if you knew the stiffness of the spring, you could show that the mass is equal to t over t squared, or let's see, it would be m equals k times t squared over 4 pi squared. That'd be how you could measure the mass of an object outside of gravity in deep space. But even if you didn't have a spring, okay, you could still measure the mass of this square. And the way you can do that really illustrates what mass is. I mean, all we're doing is applying a force, say 10 newtons, and observing an acceleration, 2 meters per second squared. That's it. Okay, and that's called the inertial mass of an object. The fact that you apply a force, a known force, any force it could be gravity, it could be the spring force, could be tension, could be thrust, could be whatever. Any force, you will observe an acceleration. And what makes mass a scalar quantity, because what makes mass a scalar quantity is that, well, one, if I double the force, I should double the acceleration. So if I apply a force of 20 newtons, I'll measure an acceleration of 4 meters per second squared, and so on. But the fact that it's a scalar means that if I rotate the direction of the applied force, say I go up 10 newtons, I still get an observed acceleration upward of 2 meters per second squared. So if I take the force and I, apply it down and to the left, it should accelerate down and to the left with the same rate. And you would then infer that the mass of this thing, if you couldn't tell, is just 5 kilograms. So that's how we measure the mass of an object. We apply a force to it and we see how it accelerates. That's all I wanted to say about mass. There's really not much to it. I mean, there's other quantities different from mass, related to mass, that are not scalars. For instance, if you're going to close a door, right, on its hinge, because we think of mass in terms of how the object responds according to applied force. Well, how the rotation of the door, it will respond differently according to not only the direction of the force, but its size as well. So if I apply a force of 10 newtons here, right, you might observe some angular acceleration, but you'll observe a different angular acceleration if I apply the force out here. Right? Obviously, the door will close faster if I apply a force further out. And there's some directions where if I apply a force over here, I won't observe anything. So this is certainly not a scalar quantity, because the result of the applied force is different in each situation, and it's not proportional to the applied force. Okay, so that's mass. Don't really want to say anything much else about mass. Let's see, moving on to gravity. And so gravity, we say a whole lot more about this in chapter 13, but we do have a law for gravity that we'll convince ourselves of in chapter 13. But basically, gravity, we say, is an attractive force between two massive objects. Now, we all know that. For all these purposes, unless we're in chapter 13, gravity will be the approximate, just pointing it straight down, just vertically downward, with magnitude, with magnitude F over G. Well, and so this, And they actually talk a little bit more about this in the section about how, there's the capital G and there's little g. Now I don't think is the appropriate time to talk about that. But so gravity is a long range force. Obviously there's whole fields of study devoted to gravity. If you weren't aware, and if you don't hear it anywhere else, one of the most recent discoveries about gravity, which actually was almost 6 years ago, was gravitational waves. Now, when a massive object accelerates through space-time, it actually sends out little ripples. And we've measured those ripples of, say, colliding like black holes or colliding neutron stars or things that are extremely, extremely dense, extremely massive, but very far away. We can see that. And then those gravitational waves actually show up as literally the space-time around us oscillating, bending. It's really interesting. But, and of course, that is not described by Newton's theory of gravity. Other topics about gravity include the bending of light around large massive objects. Another thing that's not described by Newton's theory of gravity. But Newton's theory of gravity is certainly good enough to get us to the moon, and certainly good enough to get us to Mars. Near the sun, it's not quite right. This formula kind of breaks down a little bit, and you need to slightly adjust it for the fact that the sun is so massive that it is slightly bending the space-time around it, whatever that means. We're not going to really get into that. What I do want to get into is weight. Okay, and weight we call weight a measurement, is a result of literally a measurement of another force. And so the classic example is in an elevator. I want to do some example problems related to this. So basically the idea of weight is that when you are in perhaps a reference frame that's accelerating, your weight will be different from what you expect. The first thing is like when you say weigh yourself on a bathroom scale, you just have the basic free body diagrams of gravity down and normal force up. We're going to say that the normal force is the measurement of your weight. You go to some of these old, I don't know if, I'm sure like Dillon's and stuff has them. I know Aldi has them, like the spring scales. That's to measure the weight of the fruit that's sold for vegetables. It's sold by the pound, right? You place it down. What happens in a spring scale is that the spring compresses and that counteracts gravity. So the measurement of the spring force would be the weight in that case. So it's always going to be a measurement, and it's going to be a specific force that's not gravity. And so let's go through some examples. We should really go through the book to get a better feeling of mass, weight, and gravity. So let's go back to these. Let's see, let me find them. There we go. So section 6.3, mass, weight, and gravity. So let's talk about some of these questions real quick. And depending on how we feel about them, we might even work them out. So number 17, woman has a mass of 55 kilograms. Okay, A, what is her weight while standing on Earth? B, what are her mass and her weight on Mars, where the acceleration due to gravity is 3.6 meters per second squared. Okay, so really quickly, the object's mass is an intrinsic property of the object, right? It's, it's the amount of water in your body, right? It's the amount of, it's how much bones. And sometimes people say that its mass is the amount of matter in an object. That's not quite true, actually, because at the most microscopic level, a mass is slightly different from the amount of matter in the object. Don't want to get into that, but basically, if you think of a helium atom, or helium nucleus rather, which is 2 protons and 2 neutrons, the mass of the 2 neutrons and the 2 protons by themselves is actually more than the mass of the helium nucleus. So mass is a little bit deeper than just the amount of matter in an object. But for these microscopic things, then yeah, I mean, we have that, in this case, her weight on Earth would be standing straight on Earth would be 9.8 times 55, which would be 54.8. So, or 548 newtons. I mean, we can always multiply by 2.2, you know, the classic conversion from kilograms to pounds, but kilograms are mass, pounds is the English unit of force. So don't get too caught up in that. Better to convert from newtons to pounds. And so how does the weight change then? How does the mass change on Mars? It doesn't. It's, you know, if this person flies in whatever spaceship to Mars, she'll take with her the same amount of water content, the same amount of bones, muscle with her. The weight, however, will be different. It'll be 55 times 3.76 meters per second squared. All right, 18. Okay, it takes an elevator and a skyscraper 4 seconds to reach cruising speed of 10 meters per second. A 60 kilogram passenger, goes on the ground floor. What is the passenger's weight? A, before the elevator starts moving. Okay, so this one would be good to work out, number 18. Let me just make sure the numbers right. So 10 meters per second and 4 seconds. And what's the person's mass? 60 kilograms. I'm going to mute everyone, just so there's no distractions. So yeah, number 18, let's do that one. So 6.18. So let's draw a picture. We've got 3 different cases where we're trying to find the person's weight. The first case, A, is before start. Okay, that's just, that free body diagram is just going to be the typical normal mg that cancel. So F net is 0. And the mass of the person was 60 kilograms. So what's the person's mass before the start? It's just 60 kilograms. What's the person's weight before the start? Well, in this case, weight is a measurement on the normal force. Okay, that's we're in the elevator. So F net equals 0. So in this case, the normal force, which we're saying is the measurement of the weight, is equal to mg. And so that is 60 times 9.8. I just know that off the top of my head, that's 588 newtons. It might be helpful to know what pounds is, and that is 132 pounds. So this person weighs 132 pounds before the elevator starts to ascend. Now, part B is during the ascent. So during the ascent, okay, now before we jump into it, I mean, let's just remind ourselves what we actually feel, okay? What we actually feel when we go into an elevator, go to the 3rd floor, or whatever, 10th floor, we feel pushed down, okay? We literally feel like something is pushing us down. And let's look at that from the Newton's perspective, because in this case, we got an acceleration upward. If I recall, the delta V was 10 meters per second in a time delta T of 4.0 seconds. So that means we had an acceleration of plus 2.5 meters per second squared. And just to just to confirm that we're actually going upward in this problem. I believe we are. $60 kilogram passenger. Okay, goes aboard on the ground floor of the skyscraper. Okay. So in returning to this problem, we've got that the acceleration is plus 2.5 meters per second squared because they're accelerating upward. So they feel pushed down. Let's reason about this with forces. Okay, so the free body diagram will have an F net upward. So now, how does their mass change when they're ascending? That is, they are during the ascent, is the start of the ascent. Their mass is still 60 kilograms. How does gravity change? Gravity is still the same too, because we just saw in the slides and in the textbook that the gravitational force near the surface of the Earth is still just m times a constant 9.8. And so that's still 588 newtons. Only this time, we have to have a net force of 60 times 2.5, or 150. So we have a F net of MA of plus 150 newtons. So what is that going to do to our weight then? If F net points upward, then, sorry, the Y is kind of in the way, we have to have a normal force whose magnitude is bigger than gravity. That's the sensation of everything being pushed down on us when we're accelerating upwards in an elevator. This could be that we are accelerating upwards from rest moving up, or we're careening down and then quickly coming to a stop. Both of those would be a positive acceleration. So in this case, the normal force then would be, I wasn't really precise about writing everything out. It's technically N minus mg equals plus ma. And so the normal force in this case, if it's 60 times 2.5, which is 150, plus 588 gives us 738 newtons. And what is that in pounds? It ends up being about it ends up being about 155 pounds. So just stepping in the elevator, they gain 20 pounds. Before the elevator, when the elevator was at rest, their weight was 588 newtons or 132 pounds. As the elevator is accelerating at that constant rate, their weight is 738 newtons or about 155 pounds. So their weight is measurably more while the elevator is accelerating, even though the mass and gravity are still the same. And then in the last part, what's their weight after the thing has reached cruising speed? Well, now we're back to F net equals 0. I'm sorry, there's a question about how do we find the mass of an object involving circular motion. That's a good question from chapter 8, actually, how to find the mass of an object involving circular motion. You need to know the net force and how fast the thing is rotating. The question, or sorry, to answer the question that was in the chat about mass, I'll go on this small part on the bottom left right here. Basically, the particle, if it's feeling a net force to the center, that net force is equal to m times omega squared r. So to measure the mass in circular motion, if the particle is moving in a circle, measuring the mass would amount to, you need to know the force, you need to know how far away it is from the center, and also how quickly it's rotating. So there's quite a bit of information you need to know to make a measurement of mass of an object. But certainly those things are important when we're dealing with objects of different masses, because how centrifuges work is centrifuges take little test tubes of different materials and spin them, and the ones with larger mass go further out into the test tube. And so that's a way to separate the masses. So it's certainly a non-trivial way of measuring mass. Thanks for the question. Okay, so that's a good example of weight. Let's see if there are other ones that are worth looking at. Maybe where we just move on to friction. 17, 18. Yeah, most of these other problems are kind of the same sort of elevator type problems. One thing I will mention about elevators is that, let me offer another perspective, one that the book doesn't. Let's see, I'll save this and clear. Yeah, another perspective on this, these elevator problems is that of a non-inertial reference frame. So there's two coordinate systems here. There's one that's on the ground, and then there's one that is accelerating with a certain acceleration as measured in the unprimed system. So the unprimed system is like our inertial rest frame, and the y prime system is our accelerating frame. And so how do the forces change? Well, we first have to know how these two positions are related. And sure enough, let's say at time t equals 0, at time t equals 0, we have the things match up. And then there's a constant acceleration, which means that what does physics look like in this accelerating reference frame in time? Well, let's first agree on position. Okay. This is an object, C, whatever. What's the location of that object in the different coordinate systems? Well, we have to resolve the different vectors from each other. So y prime, so at that time t equals 0, at later times, we have y prime equals y so we're trying to find the position of we're trying to find the location of object C in the prime system. And so that is actually going to be y minus 1/2 a t squared. Okay, the times are always equal. Everyone agrees on time in these two reference frames. But what they disagree on is the locations. And this is the amount, this 1/2 at squared is the amount by which their measurements of position disagree. So that, and now what if this thing is moving? What if it has a certain v sub y in the unprimed system? Well, what is v sub y prime then? It's going to equal v sub y minus at. So that would be the velocity of this object in the moving frame versus the unmoving frame. And then finally, and here's what's weird, we stop in inertial reference frames, we stop here. But if this thing has an acceleration, an a sub y, then a sub y prime, it equals the acceleration of the frame plus, or in this case, minus that acceleration between the two frames. And so if we multiply by mass, so what's the net force then? What we observe is the net force in the unprimed frame, the net force in the y frame, y prime frame, is the F net in the y frame minus what we call an inertial force, also called a fictitious force. Sorry if I didn't spell that out completely. Okay, so that's the difference. And so this is an inertial effect. The fact that you're getting pushed down as the elevator is accelerating upward is due to your fact that you're accelerating upward. Because in the reference frame of the elevator, okay, so let's look at it from two different perspectives. Let's look at it from the coordinate system that is at rest, from the y coordinate system. We see that F net points upward. Right? As the elevator is accelerating, we see that there is F net points upward. There's a normal force. There's a larger normal force, and there is a smaller gravity force. That's what we see, and so the F net points upward. That's F net in the y direction. Okay, in the rest coordinate system. Now, what about in the accelerating coordinate system? You draw the elevator again, but now we're drawing the y prime system along the moving elevator. So what is the physics here? Well, now you do come up with this inertial force. You have, well, there's my mg. I have a larger normal force. But now, see, you're not accelerating with respect to this coordinate system. Here, your F net is actually 0. And so the only way to make the F net 0 here is to say that something is pushing you down. And that something that's pushing you down is the fictitious or inertial force. We call it, fictitious FICT. And so that fictitious force that quote unquote pushes you down in the elevator is exactly the net force in the inertial system. Okay. We talk about this in the context of circular motion, chapter A, but I think this is a better way to explain it, at least for this chapter. That way you've seen it at least once of how these things work. So that is a more general way to analyze these two situations. So what's the weight? The weight in both cases is still the measurement of the normal force. Okay, in the accelerating elevator, you literally weigh more. If you're looking at the elevator, you see that the normal force is bigger than gravity. If you're in the elevator, normal force is still bigger than gravity, but we have a downward force to keep our net force in the elevator 0. So let me save that, and that will be kind of our concluding discussion about weight. Oh, what about in orbit? That's where we introduced the concept of weightlessness. There was a question about the circular motion a few minutes ago. Well, in orbit, it'd be better to just switch to the slides. The slides are pretty decent for this. We have, skip these. skip that. Aha. The so-called phenomenon of weightlessness. Well, when we're in orbit, we are accelerating towards the ground, but there's nothing pushing us up. And so there's no way to measure our weight when we're in orbit because the only thing that we have is gravity. And this is the same thing like when you, if you descend from like a high, like roller coaster or something, you see that the effect of this, the fact that there's not a large normal force means that you feel weightless. If you go over a large hill, if you take a speed bump, same thing. Okay, you momentarily feel weightless if you take the speed bump too fast. Anytime you're ever in free fall, you're weightless because you only have gravity. You don't have, if you put a scale under yourself while you're in free fall, there would be no normal force, right? If you put a spring, if you attached a spring to, a block, the spring's not going to wiggle back and forth because everything's in free fall. So when you're in free fall, you feel weightless. Okay, so that's it for that section. Some fun topics, and I'm glad we got a couple of example problems in. What we really need to do, and we really need to do some problems with friction, and we'll certainly do more in we'll do more on Friday when your homework is due. But just really quickly, there's two flavors of friction. There's static friction and kinetic friction. There's also rolling friction. Right? We talked qualitatively about what it is. This is a nice little picture to keep in mind of static friction. This picture right here of all of the, little microscopic jagged hills and peaks and valleys of objects. And think about sandpaper. Sandpaper, the more rough sandpaper, the more jagged hills and valleys you've got. And so friction is a result of molecular bonds between those two objects that come into contact. If they're pushing harder on each other, then they're more molecules per unit area are going to bond. And so the friction comes from those bonds being stuck together. So it's not really a force in the sense of, say, tension or normal or gravity. It's really a microscopic effect that we're calling a model. But at the same time, we should be aware of how to calculate these things. And they do a simple example here. If you pull on a block and it doesn't move, then the magnitude of the static friction force is equal to the tension. And that can increase or decrease until it reaches a maximum. When it reaches a maximum, then it will slip. And then the formula that we have in the textbook is for when the object actually slips. We have, let's do, we have about 5 minutes. I think that's enough to do kind of a 4 minutes. That's enough to do one example problem. So let me find one. Yeah, these exercises are all really good. And then we'll mention drag on Friday. Let's see. I'm not going to do a 5,000 kilogram, 50,000. Jeez. Let's see. Okay, here's one, number 27. Bob is pulling a 30 kilogram filing cabinet with a force of 200 newtons. Yeah. But the filing cabinet refuses to move. The coefficient of static friction between the filing cabinet and the floor is 0.8. What is the magnitude of the force, of the friction force on the filing cabinet? So, okay, so Bob is a 30 kilogram filing cabinet with a force of 200 newtons, and it won't move. So what is this friction force that's being applied to it if the coefficient is 0.8? This is number 32. Six dot 32. So the problem is easy enough to draw. We got a rough surface, and we've got the box, right, and being pulled on with a force with an applied force, but it's not moving. So if it's not moving, then F net equals 0. Oh, the mass of this thing is 30 kilograms. Yeah, the point of this problem is to really, do you understand static friction? So what's the free body diagram in this case look like? We have gravity pointing down as usual. Let's draw out y on top, x on the bottom, or x to the right. So we got gravity down. What's the magnitude of the gravity force? That is 30 times 9.8. So we got Fg equals 30 times 9.8 newtons. So that's 294 newtons. What's the normal force? Also 294 newtons. And we're applying a force to the right of 200 newtons. So what's the static friction force? Keep in mind that we have a coefficient of static friction of 0.8. So if there's a coefficient of 0.8, what's the static friction force? The temptation, and I know we're about done with the class, but I just don't want anyone to miss this subtle point here. The temptation is to say that the static friction force is just 0.8 times the normal force, which would be 294. So it'd be a little bit, let's see, 294 times 0.8, about 240, about 238 or something, about 238 newtons. Okay. Why is so it's attempting to use the formula, just coefficient times normal force to get 238 newtons. What would happen if what would happen to the free body diagram if the static friction force was 238 newtons? It would be unbalanced and the thing would accelerate to the left, right? Physically, that never happens. We don't ever pull an object to the right and somehow have it slip off and accelerate to the left. So the friction force in this case is not 238, it's actually 200. What happens is that since it's not moving, the friction force equals in magnitude the applied force. Only when the magnitude of the applied force is 238 newtons will the static friction force be mu times n. And then any more than 238 newtons, the friction changes to kinetic. And so it's not static friction anymore after that maximum value. So this mu sub n, that's F sub s max. It's a single, and it's a max. That's the important part, is that this is only the absolute, this is an expression for the absolute maximum amount of static friction force that the object can sustain, that the surface can push on the object before it slips. Any applied force larger than this one, and it's kinetic friction. Anything smaller than it, and it's equal to the actual applied force. So you got to take the static friction with some subtlety here. So the answer is certainly 200 newtons. We didn't even need to do anything to that problem. Right, I'll unshare now. Hopefully that's been a helpful couple of problems. Anybody have any questions or comments before we end? I haven't really been checking the chat. Doesn't look like there's anything new. So what we'll do on Friday is continue with chapter 6. We'll do some more examples, friction and drag, but the priority is certainly your homework questions. So bring any homework questions you've got to class on Friday, and then and then we'll keep going from there. So next week, we have a reading quiz over chapter 7 that's due tonight. I'm just going to leave it as it is. But next week is really when we'll do lots of chapter 7 problems. All right, so if nothing else, thanks for your time, everybody. I really appreciate you coming. We'll see you here on Friday.
Thank you.
Bye. Have a good day.